Good afternoon, everyone. This is the lecture for 9.2, which is Introduction to Exponential Functions. And before we start this, there's a little word problem that we will eventually encounter towards the end. And I've actually typed that up. Okay, so if you go to the Files tab within our course on Canvas, look for a file called Compound Interest Word Problem from 9.2. And that way you don't have to type it up. Okay, so what are exponential functions? Well, you have dealt with exponential expressions, right? Like this is an example of an exponential expression, right? Why? Because you have a squared right there, an exponent. So again, this is just example of exponential expressions. Really, I should put that right here, right? And then how do we figure that out? You just go, oh yeah, 7 times 7 is 49, right? But of course, you can have other weird ones, right? Like let's say if I had 6 to the 0th power, for example. Remember, anything that exists, like a real number, raised to the 0th power is automatically 1, right? Even if you had x to the 0 power, it's still 1. What about those, say, 7 to the negative 2 power, right? How do you take care of negative exponents? Remember, you have to make them positive. How do we make exponents positive? Well, we flip the base, correct? Like this. So we get 1 over 7 squared, and that becomes 1 over 49. Remember, you only flip the part that has the negative exponent being applied to it. So we had to flip the 7 because the negative 2 is being applied to it. But let's say we had, for example, 3x to the negative 9th power right here. You're not going to flip the 3 because what's that negative 9 being applied to, the x or the 3x? Just the x. So this would be 3 over x to the 9th. But what if I had, say, like 2y to the negative 5th, all in parentheses like this? Then right here, yeah, you would flip the 2 as well because the whole thing is being raised to the negative 5th power. So we would get this, but then that becomes 1 over 32 y to the 5th, right? Because 2 to the 5th is 32, y to the 5th is y to the 5th. And you can evaluate these in a calculator, but it will give you a decimal, so be careful with that. Like let's say I wanted to say 2 to the 1.5 power, because that's really hard to do, right? We can't exactly write out 2 times itself 1.5 times. So to type into the calculator, really important, because we will need it for that word problem, is you can use that caret key right here. So basically the way I would type it in on here is I would say 2 caret key 1.5. So 2 caret key, it's just above that x squared. See that? And then 1.5. And then we get this really big decimal, right? You get 2.82427, blah, blah, blah. But what we're going to do is we'll just round it off to 2 decimal places. So I'll say 2.83. Now read the directions on the homework because it may say 3 decimal places or 4 decimal places. Again, if we try another one, like if we say, I'll say pi raised to the square root of 10. Really, there's no way we could do that by hand accurately at all, right? So again, for the calculator, we would say pi right here where my thumb is, pi caret key just below the pi, and then I'm going to say square root. So to get to the square root, I got to press the blue button, right? Because it's the blue little check mark. So second square root, and then 10, and then close the parentheses. And then we get 37.34. And that's again if I round it off to 2 decimal places. Make sure you close off the parentheses as well. Okay. Now, what is all this for? Like, what if we look at a generic exponential function? Like if I look at what is the definition of an exponential function? Because all that we've been looking at so far are exponential expressions. That's just like numbers that we can simplify. But a function has some kind of variable, right? So an exponential function is actually f of x equals b to the x, where b is greater than 0 and b cannot equal 1. So an example of that could be like 3 to the x, right? or you could even have 2.4 to the x, or you could have 5 to the x minus 7, or even say 8 to the x plus 2 minus 8, like that. These are all examples of exponential functions. Why? Because where's the position of the x? Is it at the base level? Like, it's no longer down here, right? If it was down here, that would be an algebraic expression. But because our x is now the exponent, we simply have something called an exponential function. And before we do more of these problems, let's just check out, like, what does the graph of this thing look like? Like, how do we graph a generic function? Okay. How do we graph some kind of exponential function? Well, if we have no idea what it looks like, right? What is the easiest way to kind of explore that? We can make a t-table, right? So let's graph 2 to the x, for example, okay? And what I'm gonna do is just make a t-table, and I'll choose some negative values like -2, -1, 0, 1, 2, 3, something like that right there. So if we evaluate this right here, 2 to the -2 power, what is that? Well, remember, what do you do with negative exponents? You make them positive. So this is 1 over 2 squared, which is a fourth. This is 2 to the -1, which is 1 over 2 to the first. That's just a half, right? And then this is 2 to the 0, which is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. So what does this look like graphically? Let's see. So when x is -2, y is 1/4. So I'll just put, like, 1. This will be 1 right here. So a fourth is pretty close to y equals 0. So that's about right there. When x is -1, y is a half. When x is 0, y is 1. When x is 1, y is equal to 2. And then when x is equal to 2, we get to 4. And then when x is equal to 3, it goes up towards 8, right? So this is 3, 8, 2, 4, and this is 1, 2. Now, if we sketch this thing, it does something like this right here. So kind of like a unique curve. Now, what's nice about exponential functions is they all look like this right here, meaning any function in this form b to the x, it will always have this general shape right here, like this, and they have a reference point. All right, so remember we talked about the transformation functions, and we looked at all the base functions. They all shared a unique point, right? Remember that point was 0, 0. That's what they all ran through or started from. With the b to the x or the exponential function, they all have a reference point. The reference point is 0, 1. And if we think about that, it doesn't matter what b is, right? Because remember, b was a number bigger than 0, and it couldn't be 1. So if I have 10 to the 0 power, what's that? 1. If I had 1.59 to the 0 power, it's 1. Remember, any real number raised to 0 is automatically 1. So that will be your reference point. So if you had to transform it, which you're not going to have to do, but if you did, you'd use that as a reference point. And I'll work out a couple of examples right after this. But again, this is the general shape, and that's how they all look. And they all have this in common as well. So remember, if we had up and down lines, that would be a vertical asymptote. This is a horizontal asymptote. And it's at y equals 0. So anything, whether it's 3 to the x, 10 to the x, a million to the x, still gonna have that horizontal asymptote of y equals 0. Can that change? Yeah, it can if you have a transformation. So like, let's say, for example, we have, I'll do it in the blue. We want to graph y equals 2 to the x plus 4. Remember the transformation rules when you had numbers trapped inside of the x, outside of the x, like that? It's the same rules right here. this 4 is not trapped inside with the x. So remember, numbers that weren't trapped inside, that was some kind of vertical shift. So we would go up 4. Where would we go up 4 from? Well, let's use that reference point. Again, I'm just going to call this 1 right here. This is our base function, right? This is 2 to the x right here. And it has that horizontal asymptote of y equals 0. But now if I have to move everything up 4, well, what happens? That means I'll just call this 4. That means that the horizontal asymptote would shift up 4 units. So I'm going to call it HA of y equals 4. And then instead of the graph running through 0, 1, remember, because that was the reference point, it's going to run through 0, 5 instead. So I'll make a little space right here. So again, this is 2 to the x plus 4. And of course, you can have horizontal shifts, right? We can have horizontal shifts, reflection, all that stuff, right? So let's say I wanted to do in the green right here. What if we wanted to graph y equals 2 to the x minus, I'll say 5. So remember, when you have a number trapped inside with the x, that was a horizontal shift. And you go in the opposite direction. So we're not going to go left 5. We're going to go right 5. Now, how would that impact the original 2 to the x? Let's check that out. So since we're not shifting up or down, the horizontal asymptote is still y equals 0. But we need to basically slide this 2 to the x over 5 units to the right. What's that reference point that we're going to use? 0, 1. So instead of it running through 0, 1, right, if we slide everything over 5 units, it's going to, to the right 5 units, it's going to run through 5, 1 instead. Why? Because again, remember, we're only shifting the x values. The y has not changed. So it's still going to do this similar thing, this similar shape right here. So if there's no vertical shift, your horizontal asymptote's not going to change. But what if you had both transformations, right? We can have that. Like what if we had 2 to the x plus 2 minus I'll say 3, like that. So all that means is we're going left 2. It's because this is positive 2, going the opposite direction. Not because this is 2. If this was 5 to the x plus 2, you would still go left 2. Don't look at this and go, oh yeah, that's why we're going left 2. No, no, no. It's this number trapped inside of the x. Horizontally going the opposite direction. This is outside of the x, right? Not trapped inside. So that's vertical. We go in its direction and we go down 3. Now, in this case, the horizontal asymptote will change, right? Because we're going down some amount. We have a vertical shift. So here's our base function again. This is 2 to the x. It's running through 0, 1. So now if I use that as a reference point, well, first of all, we have our horizontal asymptote, right? That's our old horizontal asymptote of 2 to the x. So I need to shift that down 3 right here. And what are we basically doing with the original curve, this 2 to the x? We're shifting everything down and to the left, or down 3 units and to the left 2 units. What's the reference point that we're going to use? 0, 1. So if I knock that down 3 places, 1, 2, 3, all of a sudden we're at -2, right? Because 1 minus 3 gets you to -2. But then I have to move it left 2 spaces like that. So what is that? It's still going to look like this right here. That's the generic shape of it right there. So again, all you have to remember is that where do I base my reference point from? 0, 1 with the exponential functions. And of course, as you can see, the horizontal asymptote can shift. It will shift if you have a vertical shift. If you have no vertical shift, then it's not going to move from y equals 0. But now let's go on to the more important stuff. And really, the important thing that we want to introduce in this section is the letter E, okay? And that word problem. So an important exponential expression is E. And if you notice, your calculator even has it. I don't know if you guys can see it. It says e to the x right there, just above the ln right there. So that actually does mean something. E is actually a number. E is approximately equal to 2.71. Now, where am I getting that from? Well, if I turn on my calculator and I do second and the natural log button, and I say, and it's asking e to what power, and I type 1 in, you get 2.7182 like that. But I'm just using 2.71 right now. But that's how you access it, right? E, the E button is second ln, and you should get, see if this thing focuses, 2.718 like that. Now, what is this? What is this used for right here? This is used a lot in finance. That's actually what our word problem is going to be discussing. Mainly, it's in compound interest. Okay. So it's also used in other exponential growth problems or decay problems like population, for example, or how fast a virus spreads. Exponential functions were used to describe, for example, like how fast COVID was spreading. There's mathematical models like that. They're not linear, they're always exponential. And E, most likely, if we could look at the formula that the CDC was using, it probably would have an E in there at some point, and E raised to some crazy power or something. But we're just going to be looking at it from a financial perspective, okay? So this is the part where you want to put up that problem on, or that handout that I had from, or that I uploaded into Canvas. So let me share the screen with you really quick right here. But make sure you access it because I'm going to go back to the board. So this is the problem that I'm looking at, or that I uploaded into Canvas. It says complete, there's a table, it's coming from the homework, okay? And it says complete the table to determine the effect of the number of compounding periods when computing interest. And it's saying, oh, suppose that $7,000 is invested at 3.6% interest for 9 years under the following compounding options. And on the homework, for the first column, it's asking you, what is this N? So annually means once a year. Quarterly is obviously 4, monthly is 12, daily is 365, and continuously, I'll talk about it once we get to it. But basically, when we say compounded, that's how many times like the bank runs the numbers or processes your investment. So they basically, how often would they apply that 3.6% interest into your initial amount, meaning you would profit off of that. So annually means they only run the 3.6% once a year, or quarterly means they run it only 4 times a year. Obviously, we want it daily or continuously, because the more that they run this interest on it or apply this interest, the more money you get. So how do we figure this out? Well, the first thing that we want to do is, let me give you a formula, okay? You're not going to have to remember the formula. You just have to know how to apply it. All right. So there's 2 formulas that you need to just know how to apply. We have A equals P, and then 1 plus R over N raised to the N times T. And what does all this stuff mean, right? Like P just stands for the principal. That's what you start with, okay? If you don't know what that means, that's like the initial deposit. R is the rate, the interest rate. Really important with that, though, you want to convert it to a decimal when you're calculating. N is the number of times your principal is compounded that's compounded. I know it's looking better right there per year. T is the number of years. So just be careful because sometimes they may say, oh, for 48 months that you're leaving your money at the bank. But you're not going to put 48 in for T. You have to put 4, right? Because why? Because T's in years. 48 months is 4 years. So make sure you pay attention to something like that. And A is just the amount gained after the interest has been compounded. So again, you don't have to remember this formula, you just have to know what all these variables mean. Now that we had that though, let's go out there and try to work out this problem. So pause the video if you need to, and then copy all this stuff down. Remember that Word file can be found on Canvas as a PDF. It's a file, right? It's called Exponential Word Problem, section 9.2, under the Files tab. It's a PDF. Now, let's make the easiest way to work this out is to be organized. Make a checklist of everything that you know. They always give you everything except for the A. Okay, so they give you the P, the R, the N, and the T. But just be organized, right? P, remember, is the principal. What is that? Well, the problem says in plain English, suppose that $7,000 is invested. Well, we already have that. Done. Then it says at an interest rate of 3.6%. Remember, how do you convert? You must convert all percents into decimals. How do you do that? You slide the decimal 2 spaces to the left. That's 0.036. Remember, if there's no digit right there, you add a 0. 0.036. That's what we need to use. Now, it said for, how long are we doing this for? Invested at 3.6% interest for 9 years. So T is 9 years. All right. Now, the only thing that's going to change in these problems is the N, because remember they said, oh, figure out how much money we would get if it was compounded annually, quarterly, monthly, and so on like that. So let's go out there and work that out. So I'll start with the first one. Annually just means N equals 1. Okay, because that just means once a year, right? So how do we work that out? We are going to plug all these numbers into the formula. A equals P is 7,000. And then 1 plus the rate 0.036 over N is 1 to the N times T. That is 1 times 9. Now, how can we enter this into our calculator, right? That is the tricky part, I guess. But what you can do is you can type it in one big step. All right. So what we can do is we can say 7,000. Let me see something. I'm trying to. That's better. Yeah. So we're gonna have 7,000, and then open parentheses 1 plus 0.036 divided by 1, close parentheses, caret key right here. That's the caret key raised to the 1 times 9. But we know what 1 times 9 is. It's 9. I'm not going to write 1 times 9. And then you hit enter. So now you notice we have this amount of 9,623.56178. But this is not the actual answer because remember, this is a money problem, right? How is money described in terms of dollars and cents? So do you ever have 0.56178 cents? No, right? So you need to round this to the nearest cents. So this is $9,623.56 in this instance, right? Because we're looking at the hundreds place. We look to the right one. This is not 5 and above, so that 6 stays the same. So make sure y'all round that to the nearest cent if the problem asks you. If the problem said round to the nearest dollar, then it would be $9,624, right? Because then you look here at the 3, that's the ones place. Look right here, that's 5 and above, so you would round that up. But most of the time, it wants the nearest cents. Now, what if we did the quarterly problem, right? How would that change the problem? Well, the only thing that changes is the n becomes 4 this time. So literally, the only thing that changes is this becomes a 4 and that becomes a 4. That's it. Once we have that, we just retype the problem into the calculator. 7,001 plus 0.036 divided by 4. Close the parentheses, caret key, and then I'm going to do 4 times 9, but that's just 36. Hit enter. So then we get 96,000. I'm sorry, $9,664.51. So I'm rounding, right? Got to round off to the nearest cent right here. So 0.51, if we look at the 1, we look to the right of it, that's 4 and below, so that stays the same. Now, what if we did monthly? What's going to change? Just the n, right? Only the n's going to be 12 this time. You will have to remember what monthly means, okay? The problems are going to say, oh yeah, by the way, monthly is 12. You should know that, right? You should know that quarterly is 4, for example. But coming back to this, the only thing that changes again is the n. This is 12. This is 12 right here. All right, so we have 7,000. 1 plus, again, with the parentheses, 0.036 divided by 12. Raised to the, and 12 times 9, that's 108. So we get 9,673.84 this time. So we had to round up, right? Because 7 is bigger than 5, so this 3 is going to go up to a 4. And if you notice, our amounts, the amount of money that we're getting is slowly going up, right? That should make sense because the more we compound something or apply interest to it, the more the amount should go up, right? So if you're doing these problems and your amount's going down, then you're doing something wrong because you should always be getting more profit the more times it's compounded. And then we also had daily. So daily is 365. Only the ends are going to change. Now, how are we going to type this one in right here? So it's still 7,000, open parentheses, 1 plus 0.036 divided by 365, close parentheses, caret key. And now I'm going to use parentheses here instead because I don't know what 365 times 9 is. I can't do that in my head, but I'm using parentheses right there just to multiply it out and I'm closing it off. So be careful with that right there. And then I hit enter. And it's just slightly more. You see, like when we did it monthly, it was 9,673. Now we have 9,678. So it's not a huge jump, but it is going up, right? So we have 9,678 point 38, right? $9,678.38. We have to round that up, correct? Because I'm sorry, 6 is bigger than 5. So we round that up to 38 cents. Now for the continuously, that one right there. This one, this one is a strange case. Why? Because, and it even said not applicable. Like, what does that even mean, right? When we think about what is continuous, it's not 365 days a year. That's daily. It's not a million times a year, right? Continuous means at every single possible second, you are compounding, you are running your amount through the interest. So if we're doing it at every possible moment, it's kind of weird, but it becomes n equals infinity. So really crazy, right? Now, how does that work? Well, we can't plug infinity into that previous formula that we had. For continuous, we use this one right here, PE to the RT. So you see there's that E that comes up right there. Remember, this is only for continuous. But this formula is a lot easier, right? Because there's no 1 plus R over N and stuff like that. So how do we work this out? It's just simply A equals 7,000 E raised to the, and our rate was 0.036 times, I'll just use the asterisk to show times. I'm not gonna put X because you think it's the variable X. 0.036 times 9, because remember it was being compounded for 9 years. How would you type that into your calculator? It'd be A equals 7,000 and then E caret key 0.036 times 9. So let's type that in, right? So we have, here we go, 7,000. And then remember, to get to that E to the X, it's the blue, right? So we have to press second natural log. And there we go. And then we type in 0.036 times 9, close the parentheses and hit enter. So we get 9,678.53. So $9,678.53. We don't round it up, correct? Because this was 1 right here. So again, to type in that 7,000 E to the whatever, 7,000, to get to that E, remember, to get to any blue function on here, you have to press the second. So second E, or second natural log button, and then that pops up, right? It automatically gives you the caret key and that set of parentheses right there, that half part of it. And then 0.036 times 9 and hit enter. And there your answer will pop out. Remember, you have to round this off to the nearest dollars and cents. All right. So that covers it for 9.2. Remember, print out the handout for this. This is the word. This word problem was found in Canvas under the Files tab. It's called Exponential Word Problem for section 9.2. Okay.